So let's start with Verilog HDL. But before going into Verilog, we should know why we are using HDL and what is HDL. That is a hardware description language. So a hardware description language is a programming language which is used to model, which is used to design, and which is used to simulate digital circuits. So HDLs provide a means for engineer to describe the behavior and structure of electronic circuits and at various levels of abstraction. Like the range of abstraction can go from high level behavioral description to even low level gate level representations. Now the question arises, why were HDLs developed, right? Before going into further details about HDL and about Verilog, we should know why we are using a hardware description language, right? So prior to development of HDL, ICs were developed using manual methods which were time consuming and labor intensive. But due to the exploding complexity of digital electronic circuits since the 1970s, chip designing using manual methods started to become a tedious task because the functionality of the chip is getting increased, right? So this is where HDLs came into picture. So HDLs provide circuit designers. They provide digital logic descriptions to be performed at a high level without being tied to a specific electronic technology such as ECL, TTL, or CMOS. So some of the examples of HDL are Verilog and VHDL. So in short, HDLs were developed to address the challenges of designing complex digital systems by providing textual, high-level abstractions for describing these systems, right? Now let's come to Verilog. So Verilog is a hardware description language, as we just saw, which is used to describe the behavior and structure of the digital circuits. So Verilog is both, it is both a design entry language allowing engineers to describe the functionality of a digital circuit, and a simulation language, enabling engineers to simulate and verify the behavior of the designed circuits before fabrication. So it is supported by various electronic design automation, that is EDA tools, making it essential tool in the digital design and verification process. And if we talk more about Verilog, so it is a high level language like C or C++. So we will see in the upcoming videos that the syntax of Verilog is almost similar to C. So in this video, we are going to start with Verilog design styles. So Verilog design style is basically how we model any circuit using Verilog, right? How we are going to model the circuit using anything, how we structure and implement our Verilog code. That is what is the meaning of Verilog design styles. There can be different approaches that can be used. So let's start with that. So in Verilog, code can be written in three different design styles. We have the data flow modeling, we have the behavioral modeling, we have the gate level modeling. But there is also a fourth design style which is known as structural modeling, which can be used to model the Verilog code. So let's start with data flow modeling. In Verilog, data flow modeling describes the behavior of digital circuits by specifying how the data is going to flow through the circuit and how the data will be manipulated by various logic gates and operators which are present in the circuit. So this modeling style is referred to as data flow modeling because it focuses on the flow of data within the design and the relationships between different data elements. So this modeling style is basically used in those situations and in those circuits in which the output's Boolean expression with respect to the input is known, that is for combinational circuits. So it is used for combinational circuits. Now in data flow modeling, behavior is specified using something known as continuous assignments, which we will be seeing in the upcoming videos. So there is a assign statement which we use in the syntax, and we will see that in the next video. Now to describe the relation between input signal, intermediate signal and output signals, these assign statements will be used. So we are going to assign the output with some values which can be some operation between the intermediate signals and the input signals. And these assignments represent the flow of data from the input to the output using intermediate signals also. And this is basically used for combinational logic. So this is a pictorial representation of the combinational circuit. It will be having m inputs and it will be having n outputs, and the present output will be dependent only upon the present inputs. Now let's move on to behavioral modeling. So behavioral modeling involves describing the behavior of the digital circuit at higher level of abstraction. So focusing on the functionality and operation of the circuit rather than its internal implementation details. In behavioral modeling, designers specify how the circuit should behave in response to the different input conditions without necessarily specifying the exact timing or implementation details of the circuit. So behavioral modeling is used for those circuits in which we do not know the Boolean expression of the output but do know the behavior of the circuit. For example, a D flip-flop. So they are used majorly for sequential circuits. In behavioral modeling, we use something which are called as procedural blocks. And two major procedural blocks are initial and always blocks, which we will see again in the upcoming videos. So behavioral modeling will mostly be used for sequential circuits in which the present output not only depends upon the present input but also upon the past outputs. Now let's move on to gate level modeling. So gate level modeling is basically a lower level of abstraction in which we represent the design or of the circuit in terms of logic gates. It is not the lowest level. Switch level is basically the lowest level in which we use PMOS and NMOS transistors in order to implement the circuit. But in gate level modeling, we are using logic gates to build up the circuit, and Verilog code directly represents the physical hardware implementation of the design, and there will be a one-to-one mapping between circuit and the Verilog code, making it suitable for low-level design descriptions. So when we are talking about one-to-one, we will be just making for this circuit, we'll be just making taking the AND primitive of the Verilog, we'll be creating an instance, we'll be giving two inputs and we'll be getting one output, and then that output will be given to a instance of the OR gate, and it will have another input, and then the output of the OR gate will be given to the XOR gate, and it will be having another input, and we'll get the final output. So there is a one-to-one mapping between the two things. Now let's move on to structural modeling. So coming to structural modeling, it is basically used to connect different modules together, which can be designed either via data flow, behavioral, or gate level modeling. So in this example, we can see we are connecting module M1, module M2, and module M3 together, and these modules can be made either via behavioral or data flow modeling or gate level modeling. So let us take further example to illustrate this. Consider a full adder circuit, and we know a full adder circuit can be made using a half adder as shown. So we need two half adders and a OR gate in order to make a full adder. So if we develop a module of half adder, then we don't have to develop the whole full adder code. We can just use the half adder module in order to implement the full adder using the structural modeling. So this is it for this video. The next video we will start with data types. Thanks for watching.